Welcome back, students. Today, we're delving into the intriguing world of redox reactions, where oxidation and reduction processes play a vital role. In a redox reaction, one substance loses electrons, oxidation, while another gains electrons, reduction. Now, let's break down the half-cell reactions that occur in these processes. In our example, we have aluminum and iron electrodes immersed in a solution. The half reaction at the aluminum electrode involves the oxidation of aluminum atoms to form aluminum cations, while the half reaction at the iron electrode involves the reduction of iron cations to form iron atoms. This gives us a clearer understanding of the processes happening at each electrode. But which electrode is which? The anode, where oxidation occurs, is the aluminum electrode, while the cathode, where reduction occurs, is the iron electrode. Now, a crucial question arises. Which way do electrons flow? Electrons actually flow from the aluminum electrode to the iron electrode. This movement of electrons is what generates electrical energy. But that's not all. In the solution, cations and anions are also on the move. Cations migrate toward the cathode, and anions migrate toward the anode. This movement ensures the continuity of the chemical processes taking place. As you can see, there's a lot of dynamic activity occurring within this system, and understanding these processes opens up a world of possibilities. Now, let's proceed to our next exciting topic. Good day, students. Today, we're delving into the intriguing realm of spontaneous electron transfer and the role of potential energy in driving these processes. To start, let's take a look at why electrons transfer spontaneously from a Zn atom to a Cu2+ ion, whether directly or through an external circuit. Just like the flow of water over a waterfall, there's a remarkable comparison here. Water naturally flows over a waterfall due to the potential energy difference between the top and bottom. Similarly, electrons flow through an external circuit from the anode to the cathode in a voltaic cell because of a difference in potential energy. The anode holds higher potential energy for electrons compared to the cathode. This causes electrons to flow spontaneously towards the electrode with the more positive electrical potential. As we journey further, we'll uncover more about the fascinating world of electron transfer and potential energy interactions. Alright, students, let's delve deeper into our analogy of electron flow and the flow of water in a waterfall. Just as water spontaneously flows over a waterfall due to the difference in potential energy between its top and bottom, electrons also flow spontaneously. However, in the case of electrons, this flow is driven by potential energy differences as well. Just like water seeks the lowest point to release its potential energy, electrons move from areas of higher potential energy to lower ones. In our context, the anode holds electrons with higher potential energy compared to the cathode. This potential energy difference is what propels the electrons to move through the external circuit. Let's now explore the dynamics of electron transfer within a voltaic cell. In this context, the anode contains electrons with a higher potential energy compared to the cathode. As we've learned, nature tends to seek equilibrium and release potential energy. So, electrons flow spontaneously from the anode to the cathode, driven by this potential energy difference. This flow of electrons through an external circuit is what allows us to harness electrical energy for various applications. The cathode, with its lower potential energy, becomes the destination for these electrons. The entire process showcases the interconnectedness between potential energy, electron flow, and the fascinating world of electrochemical reactions. As we continue our journey, it's important to understand the guiding principles of electron movement. Electrons naturally move from areas of high potential energy to those with lower potential energy. In our case, electrons are flowing from the anode, where they possess higher potential energy, towards the cathode, which has lower potential energy. This movement aligns with the concept of seeking equilibrium and releasing potential energy. Furthermore, electrons are drawn towards the electrode with the more positive electrical potential. This consistent direction of electron movement plays a pivotal role in the operation of voltaic cells and the energy transfer processes we're exploring today. As we wrap up this enlightening session, let's take a moment to recap what we've learned. Spontaneous electron transfer occurs because of a significant difference in potential energy. This concept can be likened to the flow of water over a waterfall, where water moves from higher to lower potential energy points. Similarly, electrons move from the anode, with higher potential energy, to the cathode, with lower potential energy, in a voltaic cell. This movement generates an electrical current that can be harnessed for various purposes. By understanding these principles, we gain insights into the underlying mechanisms of energy transfer and the captivating interplay between potential energy and electron flow. Welcome back, students. Today, we're delving into the intriguing world of electrical potential energy and the concept of volts. Electrical potential energy is the energy associated with the position of charged particles within an electric field. We measure the difference in potential energy between two electrodes in units called volts. 1 volt, denoted as V, is defined as the amount of potential difference needed to transfer 1 joule of energy to a charge of 1 coulomb. This unit allows us to quantify the energy transferred during electrical processes. For reference, remember that an electron carries a charge of WB 10*19 coulombs. This understanding helps us grasp the energy dynamics at play in electrical systems. Let's continue our exploration into the captivating world of energy and its manifestations. Welcome back, dear students. Today, we're delving into the intriguing realm of voltaic cells and exploring the concept of cell potential. Cell potential, denoted as E-cell, is a critical term that we encounter in the world of electrochemistry. It's the potential difference between the two electrodes within a voltaic cell. Think of it as the driving force that propels electrons through the external circuit. This force, which prompts the movement of electrons, is also known as electromotive or EMF. We often refer to E-cell in volts, making it synonymous with what we commonly call voltage. To help you grasp this better, envision a voltaic cell setup where these processes take place. Now, let's move forward to unravel more about this fascinating topic. Hello, brilliant minds. Today, we're uncovering the significance of cell potential when it comes to the flow of electrons. Imagine E-cell as the powerhouse behind the movement of electrons within a voltaic cell. Electrons dance from the anode to the cathode, and this movement gives birth to something extraordinary: electrical current. This flow of electrons is what powers the devices we use daily, from the batteries in our gadgets to the intricate circuits within electronic appliances. The higher the cell potential, the greater the force pushing those electrons. This phenomenon is at the core of how batteries function and how devices are powered. So, remember, cell potential isn't just a concept, it's the driving force behind much of the technology we rely on. Greetings, inquisitive minds. Let's dive deeper into electromotive force or EMF. EMF is the spark that sets electrons in motion, propelling them through the circuit. It's the reason electrons journey from the anode to the cathode within a cell. The chemical reactions occurring at the electrodes have a direct impact on EMF. Think of EMF as the driving energy that creates the potential difference we've been discussing. This potential difference, as you've guessed, is closely tied to voltage and cell potential. EMF plays an integral role in ensuring that the devices we use, be it a simple flashlight or a complex smartphone, receive the power they need to function. Now, as we continue our exploration, keep these concepts in mind, and let's continue to unravel the mysteries of cell potential and EMF. Fantastic learners! Let's talk about how we measure cell potential. As you know, we quantify cell potential in volts, the universal unit for electrical potential difference. To establish a point of reference, we use the standard hydrogen electrode, She. This helps us compare cell potentials between different setups. We're able to calculate EMF using a clever tool called the Nernst equation, which takes into account factors like temperature and concentrations. This equation gives us valuable insights into the electrochemical reactions taking place within the cell. By understanding how to measure and calculate cell potential, we're stepping closer to mastering the intricacies of energy and electron flow. So, keep your curiosity alive as we continue our exciting journey through the world of voltaic cells and their potential. Good day, students. Today, we're delving into the intriguing world of voltaic cells and exploring the concept of standard cell potential. Now, before we dive in, let's remember a key point. The cell potential of any voltaic cell is positive. The magnitude of this potential is influenced by various factors, including the reactions occurring at the cathode and anode, the concentrations of reactants and products, and the temperature. For our discussion, we'll stick to 25 degrees Celsius as the standard temperature unless specified otherwise. And when we talk about standard conditions, we're referring to 1 molar concentration for solutions and 100.0 kPa pressure for gaseous reactants and products. The standard cell potential, often denoted as E-degree cell, is what we focus on under these standard conditions. Let's take a specific example to understand this better. Consider the zinc-copper voltaic cell shown in Figure 20.5. At 25 degrees Celsius, its standard cell potential is plus 1.10 volts. Remember, the superscript E degree indicates standard state conditions. Now, let's move forward and explore this topic even further. Welcome back, students. Today, we're delving into the intriguing realm of standard reduction potentials and their role in voltaic cells. Our journey begins with the concept of the standard cell potential, denoted as E-degree cell. This potential value hinges on the specific cathode and anode half cells involved in the voltaic cell. While it might seem like an overwhelming task to tabulate potentials for every possible cathode-anode combination, we've got a more efficient approach. We assign a standard potential to each half cell, and then these potentials become the building blocks for calculating E-degree cell. Keep in mind that the cell potential is essentially the difference between the potentials of the two half cells. To maintain consistency, the potential assigned to each electrode corresponds to the potential for reduction at that electrode. In simpler terms, we're focusing on standard reduction potentials, often denoted as E-say-red. The equation that ties everything together is E-degree cell equals E-say-red, cathode, minus E-say-red, anode, where E-degree cell represents the standard cell potential. E-say-red, cathode, is the standard reduction potential of the cathode reaction, and E-say-red, anode, is the standard reduction potential of the anode reaction. Let's move on to the next topic to explore this concept further. Good day, students. Today's topic delves into the intriguing world of standard reduction potential and how we measure it. Let's start by understanding that the direct measurement of a half-reaction standard reduction potential isn't straightforward. However, we have a clever method up our sleeves. We assign a standard reduction potential to a specific reference half-reaction. This gives us a point of comparison. Our chosen reference half-reaction is the reduction of hydrogen ion to hydrogen molecule under standard conditions. We've assigned this a standard reduction potential of exactly 0 volts. This serves as our starting point for comparison. Now, let's explore how we can determine the standard reduction potentials of other half-reactions relative to this reference value. Welcome to Topic 2, dear students. Here, we're going to delve into the heart of our reference system, the standard hydrogen electrode, or SHE for short. The SHE is a specialized electrode designed to facilitate the reference half-reaction, the reduction of H+ to H. It's crafted using a platinum wire and a piece of platinum foil coated with finely divided platinum. This platinum surface doesn't participate in the reaction, it just provides a stable platform. When we connect the SHE to our chosen reference potential of 0 volts, it becomes a reliable point of comparison for determining the standard reduction potentials of other half-reactions. Alright, everyone, let's gather around. Today, we're delving into Topic 3. This is where we're going to connect the dots, my dear students. Now, pay close attention because the standard hydrogen electrode is going to take center stage. It's like the key player in the world of standard reduction potentials. The standard hydrogen electrode, or the SHE, is our trusted reference point on the potential scale. Picture it in your mind, like a baseline for everything else. Now, we're going to compare the potentials of other half reactions to the potential of the She. When we see positive values, it means there's a leaning towards reduction. On the flip side, negative values suggest an inclination for oxidation. It's like chemistry's way of telling us which way the reaction might go. Here's where it gets interesting. The potential difference between our reference, the She, and those other reactions gives us a sneak peek into their reactivity. And guess what, my bright minds? By calculating these potential differences, we can even predict whether reactions will happen spontaneously or not. It's almost like we're detectives, discovering the secrets of chemistry. Isn't it absolutely fascinating how this simple electrode opens the doors to exploring the electrochemical world? So, my curious minds, keep those gears turning as we dive deeper into this captivating realm of science. Welcome to Topic 4, where we unravel the practical side of standard reduction potential knowledge. This understanding of redox reactions and potential differences finds applications across diverse fields. From creating batteries and designing efficient electrochemical cells to preventing corrosion, treating water, and driving industrial processes like electrolysis and metal extraction, the knowledge we gain from standard reduction potentials has wide-ranging implications. As we move forward, keep in mind the pivotal role this knowledge plays in advancing technology and our journey towards a sustainable energy future. Let's wrap up our exploration, students. On this final topic, let's review the key takeaways. We've learned how standard reduction potential serves as a powerful tool for comparison, made possible by the standard hydrogen electrode, She. Positive and negative potentials tell us about reactivity, helping us predict spontaneous reactions. And remember, these concepts find practical applications in battery technology, industries, and even solutions to environmental challenges. As we conclude this lesson, I encourage you to delve deeper into this captivating realm of electrochemistry. Keep asking questions, keep exploring, and keep igniting your curiosity. Hello, dear students. Today, we're delving into the world of electrochemical cells and a remarkable component known as the standard hydrogen electrode, or She. This electrode plays a crucial role in various electrochemical experiments. Picture this. The She consists of a platinum electrode that's immersed in a solution containing 1 Mh+ ions. Additionally, it's in contact with a stream of hydrogen gas at 100 kPa. This setup allows the She to operate as either the anode or cathode of an electrochemical cell, and that role depends on the nature of the electrode it interacts with. So, whether it's playing the role of an anode or a cathode, the She is a key player in understanding electrochemical processes. Now, let's continue our journey and explore more about electrochemical cells and their applications. Null. Welcome back, eager learners. Today, we're unraveling the mystery behind cell electromotive force, or EMF, and guess what? Our trusty standard hydrogen electrode plays a pivotal role here too. EMF is the driving force that pushes electrons through a circuit in an electrochemical cell. We can calculate this EMF by combining the standard reduction potentials of the two half cells involved. The She's potential serves as a reference point, making it possible to measure and compare the potentials of other half cells. When we put all these pieces together, we can determine the cell EMF, which gives us insights into the spontaneity and direction of the overall electrochemical reaction. So, remember, our She isn't just a bystander. It's a key player in helping us understand the energetic aspects of electrochemical systems. Get ready to explore even more exciting concepts ahead. Welcome back, students. Today, we're delving into the world of voltaic cells and exploring a fascinating spontaneous redox reaction. Our journey begins with the concept of voltaic cells, which are devices that convert chemical energy into electrical energy through redox reactions. Now, let's take a closer look at the specific reaction we're discussing. In Figure 20.9, we have a voltaic cell utilizing a standard hydrogen electrode, She. The reaction that takes place within this cell involves the oxidation of solid zinc, and the reduction of hydrogen ions, H+. This results in the formation of zinc ions, zinc and hydrogen gas, hydrogen gas. The She serves as a reference electrode to measure the cell potential. Keep in mind, spontaneous redox reactions like this one are at the heart of voltaic cells, allowing us to harness the energy they produce. So, let's move on and explore even more about these intriguing voltaic cells. Greetings, dear students. Now, let's dive deeper into the spontaneous redox reaction that powers the voltaic cell we discussed earlier. This reaction involves two crucial components, oxidation and reduction. In the oxidation half reaction, solid zinc loses electrons, forming zinc ions. On the other hand, in the reduction half reaction, hydrogen ions gain electrons and are reduced to form hydrogen gas. This transfer of electrons from zinc to hydrogen is what drives the flow of electric current within the cell. The released energy is harnessed to do useful work. It's truly remarkable how these seemingly simple chemical processes can generate electrical energy. Let's proceed to understand more about the specifics of the voltaic cell setup and its components. Hello again, students. Let's continue our exploration of voltaic cells by examining their key components. A voltaic cell consists of an anode and a cathode, each playing a distinct role. The anode is where oxidation occurs. In our example, solid zinc, Zn, undergoes oxidation, losing electrons. The cathode, on the other hand, is where reduction takes place. Hydrogen ions, H+, gain electrons to form hydrogen gas, H2. To maintain charge neutrality, a salt bridge is used. This allows ions to flow between the two half cells, ensuring a balanced electrochemical reaction. As the reactions progress, electrons flow through an external circuit, generating the electric current we can utilize for various applications. Now that we have a solid understanding of the components, let's explore some real-world applications of voltaic cells. Great job following along, students! It's time to see how voltaic cells impact our daily lives. These cells find widespread applications in batteries, powering a range of devices we use every day. From our smartphones and laptops to larger systems like automobile batteries, voltaic cells provide the energy needed to keep things running smoothly. Think about it, without these tiny powerhouses, our tech-driven world wouldn't be the same. Moreover, voltaic cells play a crucial role in the realm of renewable energy. They're employed in energy storage solutions, such as those used in conjunction with solar panels. This allows us to capture and store energy from the sun, providing a sustainable power source. As we wrap up, remember that the principles we've explored today are not just theoretical. They shape the technology shaping our future. Keep your curiosity alive as you delve into the world of energy and its incredible transformations. Congratulations on journeying through the captivating realm of voltaic cells and spontaneous redox reactions, students. Let's quickly recap what we've learned today. We began by exploring the energy-producing potential of spontaneous redox reactions within voltaic cells. This involves oxidation and reduction processes, where electrons flow to generate electric current. We discussed the significance of each component anode, cathode, and salt bridge that contributes to the overall operation of a voltaic cell. We also delved into practical applications, understanding how these cells power our devices and contribute to sustainable energy solutions. As we conclude, remember that our world thrives on the transformation of energy, and these processes are at the core of scientific and technological advancements. So, keep your curiosity ignited, and continue your exploration of the fascinating world of energy and chemical reactions. Keep up the fantastic work, and I can't wait to see you in our next class. Welcome back, dear students. Today, we're delving into the intriguing realm of half reactions and their connection to electrical potentials. It's interesting to note that while some reactions might appear as oxidations, we often write them as reductions for the sake of assigning electrical potential values. These potentials help us understand the energy changes associated with chemical processes. Remember, half reactions are versatile. They can go both ways, operating as either reductions or oxidations. In cases of equilibrium reactions, where reactants and products reach a balance, you might encounter a unique notation. It involves using two arrows, like this, one left pointing over right pointing arrows to indicate the reversible nature of these half reactions. So, whether it's reduction, oxidation, or equilibrium, these concepts shape our understanding of chemical processes and the energy transformations they entail. Now, let's dive even deeper into this captivating topic. Hello again, students. Today, we're delving deeper into the realm of energy and chemical reactions. Our next topic revolves around standard reduction potentials and the concept of intensive properties. Now, what is an intensive property, you ask? It's a property that doesn't change with the amount of substance. In the case of standard reduction potentials, this property remains consistent regardless of the stoichiometric coefficients in a half reaction. As we know, electrical potential measures potential energy per electrical charge. So, when we increase the substances involved in a redox reaction, we're simultaneously increasing the energy and charges, but the ratio of energy to electrical charge remains steady. This relationship is encapsulated by the equation 1V equals J, C, joules per coulomb. For instance, think about the reduction of zinc ions. Whether it's 10 moles of Zn2+ or just 1 mole, the standard reduction potential, denoted as E ℓ, remains the same. This consistency showcases the intensive nature of standard reduction potentials. Now, let's proceed to uncover more about the intriguing world of chemical reactions and energy transformations. Greetings once more, young scholars. Let's dive even deeper into the constant nature of standard reduction potentials, using a concrete example to solidify our understanding. Imagine the reduction of zinc ions, Zn2. Now, whether we're working with a batch of 10 moles of Zn2 or just 1 mole, the value of E ℓ, or the standard reduction potential, remains unwavering. This consistency is fascinating and showcases the intensive property of these potentials. To visualize this, let's examine the balanced half reaction. 10 Zn2, aqueous, 1 molar plus 20 electrons, E-, right pointing arrow 10 zinc, solid. The E ℓ value for this reaction is -0.76 volts. This means that no matter how many moles of zinc ions we're dealing with, the potential for this reduction remains the same. This stability plays a crucial role in understanding the behavior of redox reactions and the energy changes they involve. Ready to unravel more intriguing concepts? Let's proceed. Welcome back, dear students. Today, we're delving into the realm of voltaic cells and exploring the fascinating world of redox reactions. A voltaic cell is a device that converts chemical energy into electrical energy. Now, let's take a closer look at the correlation between the standard reduction potentials, often denoted as E ℓ, and the tendency for reduction. In a voltaic cell operating under standard conditions, the E ℓ value at the cathode is remarkably more positive compared to the E ℓ value at the anode. This difference sets the stage for spontaneous electron flow through the external circuit. Electrons journey willingly from the electrode with the more negative E ℓ value to the electrode with the more positive E ℓ value, driving the overall reaction. To visually grasp this concept, refer to Figure 20.10, which visually depicts the relationship between standard reduction potentials in the ZnCu voltaic cell, as shown in Figure 20.5. Greetings, young minds. Our journey through the electrifying world of voltaic cells continues. This time, we're immersing ourselves in the visual aspects of standard reduction potentials. Imagine a scenario where we have a ZnCu voltaic cell. This cell provides an excellent illustration of how standard reduction potentials work. On our graph, we can observe the E ℓ values for both zinc, and copper, Cupr. The cathode, which in this case is the copper electrode, boasts a more positive E ℓ value. On the other hand, the anode, represented by the zinc electrode, displays a less positive E ℓ value. This graph enables us to comprehend the electron flow, as electrons happily traverse from the anode to the cathode, creating a flow of electricity along the way. Hello again, inquisitive minds. Let's delve deeper into the driving forces behind the mesmerizing electron flow within voltaic cells. As we've learned, the standard reduction potentials, E-read values, play a pivotal role in dictating the direction of electron movement. When we examine these E-read values, we're essentially peeking into the equilibrium constants of the reactions. The more positive E-read value at the cathode signifies a reaction more inclined towards reduction, encouraging electrons to travel in that direction. This dynamic interplay of redox reactions not only fuels the flow of electrons but also serves as a cornerstone for energy conversion. By harnessing these chemical reactions, we can tap into the potential of generating electrical energy to power various devices and systems. Welcome to the finale of our voltaic cell exploration, young scholars. Let's unveil the incredible potential these cells hold in our modern world. Voltaic cells find their way into numerous practical applications. One of the most prominent realms is the realm of batteries. Batteries rely on redox reactions to provide us with a convenient source of portable power. Think about the gadgets you use every day, from smartphones to laptops, all powered by these ingenious devices. Additionally, as our planet embraces sustainable energy solutions, voltaic cells play a significant role in harnessing clean energy. Solar panels, for instance, utilize similar principles to convert sunlight into electricity. So, remember, these seemingly complex redox reactions are at the heart of some of the most essential technologies shaping our lives today. Welcome back, students. Today, we're delving into the realm of oxidizing and reducing agents. These agents play a crucial role in chemical reactions by either gaining or losing electrons. Let's start by looking at half reactions and their tendencies to undergo reduction. In front of us, we have Table 20.1, which lists these half reactions in a specific order. Take note that the order is based on the decreasing tendency to undergo reduction. Now, focusing on F2, which is positioned right at the top of the table. This means it boasts the most positive value for E-degree read. As a result, F2 takes the lead as the species most easily reduced, making it the strongest oxidizing agent within this context. Keep this insight in mind as we explore further. Hello, dear students. Today, we're delving deeper into chemical reactions and exploring the roles of oxidizing and reducing agents. It's like chemistry's way of playing a balancing act. Oxidizing agents are present on the product side of reactions, while reducing agents are found on the reactant side. This means that only the substances on the product side can serve as reducing agents, while those on the reactant side can be oxidizing agents. Let's take hydrogen, H2, and active metals, such as alkali metals and alkaline earth metals, as examples of reducing agents. Even metals like zinc, Zn, and iron, Fe, come into play, using their negative E-degree read values as a basis. However, it's important to note that storing solutions of reducing agents can be quite a challenge due to the ever-present oxygen, O2, which is a potent, oxidizing agent. Now, let's continue our journey into the intricate world of chemical reactions and energy transformations. Welcome back, young scholars. Our exploration into reducing agents continues. Now, let's discuss some challenges and applications associated with these powerful substances. Storing solutions of reducing agents can be quite tricky due to the ever-watchful oxygen, which is a skilled oxidizing agent. Despite this challenge, reducing agents find their way into various industrial processes. From metallurgy to metal extraction, these agents play a vital role in shaping the materials and products we rely on. As our world strives for sustainability, understanding redox reactions and the role of reducing agents becomes even more crucial. So, let's keep our minds open as we move forward, discovering how these agents contribute to the fascinating realm of chemical transformations. Greetings, attentive learners. Today, we're unveiling the captivating world of redox reactions and the energy exchange that accompanies them. At the heart of redox reactions lies the transfer of electrons between reactants. Electrons dance their way from reducing agents to oxidizing agents, creating a mesmerizing exchange of energy. It's like a dynamic duet between these agents. As electrons move, so does energy, and this relationship between redox reactions and energy exchange is a cornerstone of our discussion. Keep in mind that the very concept we're exploring today is intricately tied to the energy production we touched upon earlier. With each electron transferred, a step towards energy transformation is taken. Exciting, isn't it? Let's proceed with our exploration, diving even deeper into the intricacies of redox reactions. Hello again, inquisitive minds. Our journey into redox reactions continues with a closer look at oxidation and reduction potentials. E-degree read, as we call it, is a measure of how eager a substance is to either lose or gain electrons in a redox reaction. Imagine it as a substance's personality trait in the world of chemistry. To help us measure these tendencies, we have the standard hydrogen electrode, She, as our trusty reference point. E-degree read values are like a ranking system for substances' eagerness to participate in redox reactions. The higher the E-degree read value, the stronger the oxidizing agent it becomes. This ranking also gives us insights into the spontaneity of redox reactions. So, as we move forward, keep an eye out for these potentials, as they hold the key to understanding the chemistry of energy transformations. Welcome, curious learners, to a chapter where chemistry intertwines with the very fabric of life. Today, we're exploring the magnificent occurrence of redox reactions in the realm of nature. From the intricate dance of cellular respiration to the sunlit symphony of photosynthesis, redox reactions play a vital role in powering life's processes. Imagine the intricate exchange of energy as electrons shuffle between reactants, driving the very essence of life itself. These reactions aren't just confined to test tubes. They're the heartbeat of ecosystems and the essence of energy flow. As we delve deeper, remember that redox reactions are not only fascinating but also essential for the sustainability of life on our precious planet. As we conclude our journey today, we've delved into the captivating world of the Hall-Hérold process and its impact on aluminum production. From the challenges of early aluminum extraction to the revolutionary electrolytic process developed by Charles M. Hall and Paul Hérold, we've witnessed the evolution of an industry. This process not only made aluminum more affordable but also paved the way for advancements in technology and energy efficiency. Remember, every innovation begins with a problem to solve and a determination to find a better way. Keep exploring, keep questioning, and who knows? You might just be the next innovator to shape the future. Welcome, dear students, to a riveting discussion on redox reactions and the intriguing world of oxidizing and reducing agents. Our journey today begins with an overview of redox reactions, where substances exchange electrons to transform into different forms. Let's delve deeper into the concept of oxidizing and reducing agents. In the top half reactions of Table 20.1, the substances on the reactant side are the most readily reduced species, making them the strongest oxidizing agents. On the flip side, substances on the product side of these reactions are the most challenging to oxidize, marking them as the weakest reducing agents. Figure 20.11 visually encapsulates this information, showcasing the correlation between these substances. For instance, F-gas is identified as the strongest oxidizing agent, while F-ions stand as the weakest reducing agent. Now, let's move on to the lower half reactions in Table 20.1. Continuing our journey. Let's delve into the lower half reactions present in Table 20.1. In this scenario, the reactants, such as Li-Pa and ions, take the stage as the most challenging to reduce. Consequently, they serve as the weakest oxidizing agents in this context. Now, what about the products of these reactions? Li-SNF, in particular, emerges as a species that is remarkably easy to oxidize, making it the strongest reducing agent in this domain. This fascinating interplay between substances is a fundamental aspect of redox reactions. By understanding the strengths and weaknesses of these agents, scientists can predict and control chemical processes with precision. As we unravel the intricacies of redox reactions, remember that these reactions play a pivotal role in various natural and industrial processes, contributing to the energy transformations that shape our world. Stay engaged as we continue our exploration. Hello, dear students. Today, we're delving into the world of voltaic cells and exploring a fascinating reaction that takes place within them. Voltaic cells are devices that harness the energy produced during redox reactions to generate electrical power. Our journey begins with understanding the concept of standard cell potential, which measures the potential difference between two half-cell reactions. This measurement gives us insight into the overall feasibility of the redox process. Now, let's apply this knowledge to the specific reaction involving PD and CD. This reaction has a measured standard cell potential of plus 1.03 volts. So, let's uncover the half-cell reactions that make this process possible. Welcome back, students. Now, let's dive deeper into the half-cell reactions that make our voltaic cell work. In any redox reaction, we have two half reactions, oxidation and reduction. At the anode, which is the negative electrode, oxidation occurs. In our case, the oxidation half reaction involves palladium chloride ions losing electrons to become palladium metal. On the other hand, at the cathode, the positive electrode, reduction takes place. Here, cadmium ions accept electrons and transform into cadmium metal. These two half reactions work together to create a flow of electrons and, consequently, electricity. But what about the standard reduction potential for palladium? Let's move on to the next topic to find out. Great job, everyone! Now, let's unravel the mystery behind the standard reduction potential of the PD half reaction. E degree stands for the standard reduction potential, a measure of how easily a species gains electrons. Using data from Appendix E, we can find the standard reduction potential for PD ions to PD metal. By subtracting the reduction potential of PD from that of CD, we can determine the E degree value for the PD half reaction. This value helps us understand the tendency of PD ions to gain electrons and undergo reduction. With this information, we're getting closer to fully grasping the workings of our voltaic cell. Hello, eager learners. Now that we've covered the reactions and potentials, let's visualize how our voltaic cell is set up. Picture a voltaic cell with two half cells, each containing one of the reactions we discussed earlier. The anode, where oxidation occurs, is the source of electrons. The cathode, where reduction happens, is the destination for those electrons. Electrons flow from the anode to the cathode through an external circuit, generating an electric current. But wait, we can't forget about maintaining a charge balance. That's where the salt bridge comes into play. It allows ions to move between the half cells, preventing a buildup of charge. Our journey through voltaic cells and their amazing potential continues. Hello, dear students. Today, we're diving into the fascinating world of calculating standard electromotive force, or EMF, for various reactions. This concept is essential for understanding the energy changes that occur during chemical reactions. By determining the standard EMF, we can predict whether a reaction is spontaneous or non-spontaneous. Let's embark on this journey together. Alright, students, let's start by calculating the standard EMF for reaction A. The reaction involves hydrogen gas and fluorine gas combining to form hydrogen ions and fluoride ions. We'll need to use the standard reduction potentials from Appendix E to calculate the EMF. Pay close attention to the values as we work through this process together. Great job, class! Now, let's move on to calculating the standard EMF for reaction B. This reaction involves the interaction between copper ions and a solid calcium. We'll be using the standard reduction potentials from Appendix E once again. Pay attention to the signs of the values, as they're crucial in our calculations. Fantastic, dear students. Now, let's tackle the calculation of standard EMF for reaction C. In this case, we're dealing with a reaction involving iron ions and a solid iron. By using the standard reduction potentials from Appendix E, we can determine the EMF and understand the energy changes that occur during this process. Welcome back, everyone. Our journey isn't complete without calculating the standard EMF for reaction D. This reaction might seem complex, involving multiple components and changes. But fear not. With the help of the standard reduction potentials from Appendix E, we'll break it down step by step and arrive at our EMF value. Bravo, class! You've successfully journeyed through the world of calculating standard EMF for various reactions. Remember, this concept is a key to understanding the energy changes in chemical reactions. By grasping the EMF values, we can predict whether reactions occur spontaneously. I encourage you to continue exploring the fascinating realm of electrochemistry, where these concepts play a vital role. Keep up the excellent work, and keep that curiosity alive. Good day, students. Today, we're delving into the intriguing world of voltaic cells and their fascinating components. Our journey begins by exploring the setup of a specific voltaic cell. In one beaker, we have a strip of cadmium metal immersed in a solution of CD-nitrite. In the other beaker, a platinum electrode is placed within a sodium chloride solution, with chlorine gas, chlorine, being bubbled around the electrode. These two beakers are connected by a salt bridge, which plays a crucial role in maintaining charge balance. Now, let's move on to understanding the roles of the electrodes within this cell. Alright, students, let's dive deeper into the roles of the electrodes in our voltaic cell. We have the cadmium metal electrode and the platinum electrode. Now, within a voltaic cell, we have what we call an anode and a cathode. The anode is where oxidation occurs. This means that the anode loses electrons. On the other hand, the cathode is where reduction takes place. Here, the cathode gains electrons. Determining which electrode is which in our setup is crucial, as it guides the direction of electron flow and the overall functioning of the cell. Let's find out which electrode serves as the anode and which one is the cathode in our voltaic cell. Great job, students! Now, let's uncover the roles of our electrodes in the voltaic cell. In this setup, the cadmium electrode serves as the anode. Here, oxidation occurs, and the cadmium metal loses electrons, leading to the formation of Cd2+ ions in the solution. On the other hand, the platinum electrode serves as the cathode. Reduction takes place here, as the chlorine gas, Cl2, is reduced to form Cl ions in the solution. This electron flow from the anode to the cathode is what drives the electric current within our voltaic cell. We've uncovered the roles of these electrodes, but our exploration doesn't end here. Let's now discuss the unsung hero of our voltaic cell setup, the salt bridge. This bridge plays a vital role in maintaining the balance of charges within the cell. You see, as electrons flow from the anode to the cathode, charges can start to accumulate. The salt bridge comes to the rescue by allowing ions to migrate between the two solutions, which helps counteract any excess charge buildup. This ensures that our voltaic cell can continue operating smoothly. The salt bridge might seem like a small component, but its role is crucial for the proper functioning of the cell. Keep up the great work, students. Hello again, students. Let's shift our focus towards the intriguing evolution of electric vehicles. Surprisingly, electric cars have been in existence since the late 1800s. However, during that time, they had limited range and faced challenges due to high battery costs. These limitations made it difficult for them to compete with the internal combustion engine that was dominating the market. Fast forward to the present, and we witness an exciting transformation. New developments in lithium-ion battery technology, coupled with the decreasing cost of lithium, have paved the way for electric vehicles to make their mark in the domestic car market. Even though the cost of batteries remains a significant consideration, it's worth noting that over the last decade, since 2010, the cost has plummeted by an astonishing 600%. Electric vehicles also boast impressive engine efficiencies, hovering around 70%. This efficiency is notably higher than traditional petrol or diesel engines, which utilize only about 15 to 20% of the fuel energy to move the vehicle. For an in-depth exploration of electric vehicles, you can refer to the chemistry put to work box on page 987. As we delve further, keep in mind the remarkable progress electric vehicles have made in the critical role of battery technology in this transformation. Welcome back, dear students. Today, our journey takes us into the intricate world of redox reactions and the fascinating link between redox potentials and changes in Gibbs free energy, symbolized as delta G. Our goal is to establish a connection between the standard electrode potential, E, Gibbs free energy change, delta G, and equilibrium constant, K. To achieve this objective, we need to delve into the electrochemical aspects of reactions. Redox reactions involve the transfer of electrons, and understanding this process is pivotal to comprehending how energy changes occur during chemical transformations. As we progress, we'll uncover how redox potentials align with alterations in energy and equilibrium constants. Imagine electrons dancing between species, causing shifts in energy levels and equilibrium positions. Let's embark on this enlightening exploration. Welcome back, students. Today, we're delving into a captivating topic: spontaneous redox reactions and the incredible energy they produce. In our study of voltaic cells, we've noticed a fascinating phenomenon. Voltaic cells harness the power of spontaneous redox reactions to generate a positive cell potential. How do we determine whether a given redox reaction is spontaneous? Well, armed with half-cell potentials, we can unravel this mystery. Here comes the intriguing equation 20.8, which goes beyond just voltaic cells. It's a versatile equation that allows us to describe redox reactions in various scenarios. Let's break it down. The equation looks like this: E degree equals E degree sub red for the reduction process minus E degree sub red for the oxidation process. What does this equation tell us? It unveils the potential difference between the two half-cell reactions, shedding light on the spontaneity of the overall redox process. As we journey through this equation and its implications, remember that redox reactions hold the key to unlocking a world of energy transformations. Get ready to explore further. Welcome back, students. In our exploration of energy and chemical reactions, we've now come to the intriguing realm of voltaic cells and the role of spontaneous redox reactions. Voltaic cells are fascinating devices that harness the power of these reactions to generate electrical energy. But how do we determine if a redox reaction is spontaneous? Well, this is where half-cell potentials come into play. These potentials provide us with valuable information about the tendency of a reaction to occur. And guess what? We have equation 20.8 to aid us in this journey. This equation is a powerful tool that helps us assess redox reactions, not only in voltaic cells but in various contexts. It's formulated as follows: E degree equals E degree of the reduction process, minus E degree of the oxidation process. This equation provides insights into whether a given redox reaction will proceed spontaneously. Let's delve deeper into the application of this equation and its significance in understanding chemical reactions. Hello again, dear students. Today, we're taking a closer look at the concept of half-cell potentials, and how they play a pivotal role in determining whether a redox reaction is spontaneous. When we measure half-cell potentials, we're essentially gauging the readiness of a substance to undergo reduction or oxidation. A positive E degree value suggests that the reduction process is favored and that the reaction is likely to occur spontaneously. On the other hand, if we encounter a negative E degree value, it's an indication that the oxidation process is favored, and the reaction might not proceed on its own. By comparing the E degree values of the reduction and oxidation processes, we can make insightful predictions about the spontaneity of the overall redox reaction. Now, let's move forward to explore more intriguing aspects of chemical reactions and energy production. Greetings, young minds. Our journey into the world of chemical reactions continues with the unveiling of equation 20.8. This equation is a valuable tool that encapsulates the essence of redox reactions, not only in voltaic cells but in various contexts. Allow me to reiterate its formula. E degree equals the E degree value of the reduction process minus the E degree value of the oxidation process. This equation serves as a guiding light to discern the spontaneity of a redox reaction. When the calculated value is positive, the reaction tends to occur spontaneously, releasing energy in the process. Conversely, a negative value suggests a non-spontaneous reaction that requires an external energy source to proceed. Equipped with equation 20.8, we can unravel the secrets of chemical reactions and their potential to drive energy transformations. Prepare yourselves for more captivating insights into the world of chemistry. Welcome back, students. Today, we're delving into the intriguing world of electrolytic cells and the captivating relationship between the amount of substance transformed and the electrons involved. Imagine a scenario where we have a half reaction occurring within an electrolytic cell. In this scenario, the quantity of substance reduced or oxidized is directly linked to the number of electrons that enter the cell. Now, let's talk about something known as charge. In electrical circuits, like those found in electrolytic cells, charge is measured in coulombs. Did you know that the charge on 1 mole of electrons is an astounding 96,485 coulombs? That's quite a charge. Speaking of which, a coulomb is defined as the amount of charge passing a point in a circuit in 1 second when the current is 1 ampere. In other words, it's like the currency of electrical charge. So, how do we calculate the number of coulombs passing through a cell? Simple. Just multiply the current in amperes by the elapsed time in seconds. Coulombs equal amperes times seconds. Our visual aid, figure 20.30, gives us a clear picture of how substances transform and connect to the quantity of electrical charge used in electrolysis. Keep in mind that these relationships are also applicable in voltaic cells. Remember, electrons play a crucial role in electrolysis reactions, almost like reagents guiding the transformation of substances. Let's move on and explore further. Good day, students. Today, we're going to delve into a fundamental concept in chemistry, the understanding of metal activity series using standard reduction potentials. As we've previously learned, metals in the activity series, as presented in Table 4.5, exhibit a particular behavior when they interact with each other. Brace yourselves, as we're about to uncover the mechanism behind this fascinating phenomenon. We'll start by revisiting standard reduction potentials, a concept that aids us in deciphering the activity series puzzle. This series ranks metals based on their oxidation reactions, with the most potent reducing agent at the top and the weakest at the bottom. It's worth noting that this arrangement is the reverse of what we see in Table 20.1. Now, let's dive into a specific example to solidify our understanding. Nickel and silver, for instance, are both part of this activity series. However, nickel rests above silver in the hierarchy, implying that it's the stronger reducing agent. Why is that? Well, my dear students, the key lies in the fact that a reducing agent gets oxidized in redox reactions. This leads us to the conclusion that nickel is more prone to oxidation than silver. Can you feel the pieces of the puzzle coming together? Keep your curiosity alive as we journey further into the intricacies of standard reduction potentials and metal activity series. Welcome back, students. Today, we're delving into the realm of standard reduction potentials and the fascinating concept of the activity series of metals. This topic helps us understand how different metals interact in redox reactions. To start off, let's recall that any metal in the activity series, as seen in Table 4.5, undergoes oxidation when it comes into contact with ions of any metal situated below it in the series. Now, what's the connection between this rule and standard reduction potentials? Well, the activity series is actually organized based on the oxidation reactions of these metals. The list goes from the strongest reducing agent at the top to the weakest at the bottom, which is the reverse of the order in Table 20.1. Let's take an example: nickel and silver. In the activity series, nickel is above silver, indicating that nickel is the stronger reducing agent. Since a reducing agent gets oxidized in redox reactions, this means nickel is more prone to oxidation compared to silver. This relationship becomes clearer when we examine standard reduction potentials. So, let's proceed to explore the intricacies of this relationship and how it impacts the behavior of metals in redox reactions. Hello again, students. Our journey into the world of energy conversion through redox reactions continues. When it comes to photosynthesis, photon absorption by chlorophyll is the initial spark. This absorption sets off the release of electrons in photosystem I. These electrons embark on an exciting journey along an electron transport chain. This journey not only generates energy but also facilitates the reduction of NADP to NADPH. As a quick reminder, native serves as a crucial reducing agent used by cells for various processes. Meanwhile, as part of this intricate dance, photosystem II steps in to replace the electrons lost by photosystem I. How does it do this? By oxidizing water into oxygen and hydrogen ions. Keep in mind that the intricacies of this process are even more remarkable than our overview. Let's delve deeper into these mechanisms. Hello again, dear students. Now that we've introduced the connection between the activity series and standard reduction potentials, let's delve deeper into the world of reducing agents and oxidation. In the context of the activity series, a reducing agent refers to a substance that has the ability to facilitate the reduction, gain of electrons of another substance. Interestingly, in redox reactions, a reducing agent itself gets oxidized. This is where the activity series comes into play. The sequence of metals in the activity series determines the strength of the reducing agent. A metal higher in the series has a greater tendency to be oxidized and, in the process, act as a reducing agent for other substances. This profound relationship between the activity series and oxidation reactions showcases how metals interact based on their electron transfer capabilities. As we move forward, we'll unravel more about the principles that govern these reactions and explore real-world applications. As we conclude our journey today, we've delved into the captivating world of the Hall-Hérold process and its impact on aluminum production. From the challenges of early aluminum extraction to the revolutionary electrolytic process developed by Charles M. Hall and Paul Hérold, we've witnessed the evolution of an industry. This process not only made aluminum more affordable but also paved the way for advancements in technology and energy efficiency. Remember, every innovation begins with a problem to solve and a determination to find a better way. Keep exploring, keep questioning, and who knows, you might just be the next innovator to shape the future. Welcome, students, to a captivating journey through redox reactions and the intriguing world of energy changes. Today, we'll delve into the process of balancing redox equations and explore how we can quantify the energy transformations that take place. Our first step involves understanding the concept of standard EMF, or the electromotive force. This quantifies the potential energy change that occurs as electrons flow from one substance to another during a redox reaction. Now, let's roll up our sleeves and get ready to tackle the exciting challenges of calculating standard EMF, increment g degree, and equilibrium constants for various redox reactions. Alright, students, let's dive right into our first redox reaction. We're exploring the oxidation of aqueous iodide ion to solid iodine. Here's the balanced equation for this process. Remember, in the world of redox reactions, electrons are the key players. We can use the Nernst equation to calculate the standard EMF, which tells us about the potential energy change. Additionally, we'll calculate the increment g degree at 298 K, which provides insights into the spontaneity of the reaction. Last but not least, we'll determine the equilibrium constant K at 298 K to understand the distribution of products and reactants at equilibrium. Great job, students! Now, let's move on to our second example, the oxidation of copper ion to copper ion in acidic solution. We'll begin by writing the balanced equation for this redox reaction. As always, our trusty tool, the Nernst equation, comes into play to calculate the standard EMF. This gives us a glimpse of the energy changes occurring during the electron transfer. But we're not stopping there. We'll calculate increment g degree at 298 K, shedding light on the feasibility of the reaction. And of course, we'll determine the equilibrium constant K at 298 K, revealing the balance between reactants and products at equilibrium. Null. Bravo, students! As we wrap up our exploration of redox reactions, let's take a moment to reflect on the role of equilibrium constants in the world of energy transformations. Equilibrium constants provide crucial information about the distribution of reactants and products in a system at equilibrium. By understanding the relationship between equilibrium constants and energy changes, we gain deeper insights into the driving forces behind chemical reactions. To cap off our journey, let's put our knowledge to the test and calculate increment g degree and e degree for a 2-electron redox reaction at 298 K. This will bring together everything we've learned about energy, reactions, and equilibrium. Welcome, students! Today, we're delving into the fascinating world of redox reactions and how they play a crucial role in energy conversion within various metabolic processes. Let's start with a remarkable example: photosynthesis. During photosynthesis, chlorophyll absorbs photons, leading to the release of electrons in photosystem I. These electrons journey down an electron transport chain, causing the reduction of nicotinamide adenine dinucleotide phosphate (NADP) to native, an essential reducing agent for cells. Notably, the lost electron in photosystem I gets replaced by photosystem II, which achieves this by oxidizing water into oxygen and hydrogen ions. Remember, this process is far more intricate than our simplified explanation, but at its core, it relies on redox reactions and concentration gradients. Now, let's explore further to gain a deeper understanding of these concepts. Hello again, students. Our journey into the world of energy conversion through redox reactions continues. When it comes to photosynthesis, photon absorption by chlorophyll is the initial spark. This absorption sets off the release of electrons in photosystem I. These electrons embark on an exciting journey along an electron transport chain. This journey not only generates energy but also facilitates the reduction of NADP to NADPH. As a quick reminder, native serves as a crucial reducing agent used by cells for various processes. Meanwhile, as part of this intricate dance, photosystem II steps in to replace the electrons lost by photosystem I. How does it do this? By oxidizing water into oxygen and hydrogen ions. Keep in mind that the intricacies of this process are even more remarkable than our overview. Let's delve deeper into these mechanisms. Hello once again, eager learners. As we explore the captivating world of photosynthesis and redox reactions, let's acknowledge the complexity of this process. Photosynthesis is a symphony of intricate steps and reactions, all orchestrated to harness and convert energy. The electron transport chain takes center stage, facilitating the flow of electrons and the production of native, a key player in cellular processes. Concentration gradients also play their part, contributing to the generation of energy. Don't forget the critical role of photosystem II, which ensures the continuity of electron flow by extracting electrons from water molecules, leading to the release of oxygen and hydrogen ions. It's important to recognize that the importance of redox reactions extends beyond photosynthesis and is fundamental to various metabolic pathways. Let's continue our exploration and dive deeper into the remarkable world of energy conversion. Welcome, dear students. Today, we're delving into the realm of voltaic cells and their behavior under non-standard conditions. We've previously explored how to calculate the electromotive force, EMF, of a cell when reactants and products are at standard conditions. Now, as we discharge a voltaic cell, something interesting happens. The reactants are used up, and products are formed, leading to changes in concentrations. Consequently, the EMF of the cell starts to decrease progressively. Eventually, the EMF reaches a point where it equals zero. At this juncture, we declare that the cell has reached the end of its energy-producing journey and is dead. But worry not, for there's more to uncover. Let's proceed to understand how the EMF generated under these non-standard conditions can be mathematically calculated. Our guide on this journey is none other than Walther Nernst, a visionary chemist from Germany, who bestowed upon us a fundamental equation that underpins the study of electrochemistry. Welcome, dear students. Today, we're delving into the realm of voltaic cells and their behavior under non-standard conditions. We've previously explored how to calculate the electromotive force, EMF, of a cell when reactants and products are at standard conditions. Now, as we discharge a voltaic cell, something interesting happens. The reactants are used up, and products are formed, leading to changes in concentrations. Consequently, the EMF of the cell starts to decrease progressively. Eventually, the EMF reaches a point where it equals zero. At this juncture, we declare that the cell has reached the end of its energy-producing journey and is dead. But worry not, for there's more to uncover. Let's proceed to understand how the EMF generated under these non-standard conditions can be mathematically calculated. Our guide on this journey is none other than Walther Nernst, a visionary chemist from Germany, who bestowed upon us a fundamental equation that underpins the study of electrochemistry. Let's get down to the heart of the matter, shall we? The man of the hour is Walther Nernst, whose brilliance gave us the Nernst equation. This equation allows us to grasp the EMF of a cell under non-standard conditions by considering changes in concentrations. In its elegant form, the equation is E equals E naught minus 0.0592 divided by N, multiplied by the logarithm of Q. Here, N represents the number of moles of electrons transferred in the cell reaction. The variable Q is the reaction quotient, which takes into account the ratio of product concentrations to reactant concentrations. This equation gives us a powerful tool to predict and comprehend the behavior of voltaic cells when reactant and product concentrations aren't at their standard levels. Let's continue our journey to see this equation in action. It's time to roll up our sleeves and put the Nernst equation to work. Imagine a scenario where the concentrations of reactants and products are no longer at their standard states. To determine the EMF of the cell in such cases, we follow a simple yet powerful process. Step 1 involves calculating the reaction quotient, Q, by comparing the concentrations of products and reactants. Step 2 is where the Nernst equation shines. We take our calculated Q, plug it into the equation, along with the other constants, and voila! We get the EMF of the cell under non-standard conditions. This approach allows us to analyze various cell reactions and predict their behavior when concentrations deviate from standard values. Ready to see some examples? Let's explore. Hello there, students. Today, we're delving into an intriguing topic, the Nernst equation, which sheds light on the impact of concentration on cell electromotive force or EMF. But before we dive into the equation itself, let's quickly recap some essential concepts. You're already familiar with free energy change, ΔG, in chemical reactions. Well, this ΔG is linked to the standard free energy change, ΔGO, for the reaction. Now, let's introduce the star of our show, the Nernst equation. This equation allows us to explore how changes in concentration influence cell EMF. It goes like this. ΔG equals ΔGO plus the product of the gas constant, R, temperature, and the natural logarithm, of the reaction quotient. This equation is a powerful tool that helps us understand the connection between concentration and cell EMF. Keep in mind that it plays a crucial role in electrochemistry, giving us insights into how reactions happen in various conditions. Ready to uncover more? Let's proceed to the next topic. Welcome back, students. In our previous topic, we introduced the Nernst equation as a tool for understanding the effect of concentration on cell EMF. Now, let's dig deeper into the interpretation of this equation. The equation shows how the actual free energy change, increment g, is related to the standard free energy change, increment g degree, and the reaction quotient, q. By analyzing these components, we can determine whether a reaction will proceed spontaneously or not, based on the concentrations of reactants and products. The fascinating part is that changes in concentration can influence the direction and spontaneity of reactions. The temperature, T, and gas constant, R, also play significant roles in shaping the outcomes. This equation is crucial for predicting the behavior of electrochemical cells and understanding how they function under different conditions. As we move forward, we'll explore more real-world applications and dive into practical examples that bring this equation to life. Fantastic to have you here, students. Now that we've laid the foundation of the Nernst equation, let's explore some exciting real-world applications. Brace yourselves for a journey into the realm of practicality. First up, we have batteries. Yes, the ones that power your devices. The Nernst equation helps us understand how the potential of a battery cell changes as the concentrations of reactants and products inside the cell change over time. This insight is crucial for optimizing battery performance and predicting its behavior. Moving on, did you know that the Nernst equation plays a pivotal role in pH measurement using electrodes? Electrodes in solutions of different pH levels experience potential changes, and this phenomenon can be quantified using the equation. But the excitement doesn't stop there. In the realm of biology, the Nernst equation comes into play in understanding processes like nerve impulses and ion gradients across cell membranes. These gradients are vital for various physiological functions. So, as you can see, this equation isn't just a theoretical concept. It's a tool that guides us through a world of practical applications. Let's continue our exploration. Hello, curious minds. As we continue our journey through the Nernst equation, let's take a moment to talk about its limitations and the real-world considerations that come into play. While the equation is incredibly powerful, it's important to remember that it's based on certain assumptions and ideal conditions. In the real world, electrochemical cells often face complexities that can't be fully captured by the equation alone. Factors like electrode polarization, which occurs due to resistance at the electrode-electrolyte interface, can impact the accuracy of our predictions. Moreover, the Nernst equation assumes ideal behavior, which may not always hold true in complex systems. So, while the equation provides us with valuable insights, it's crucial to keep in mind that real-world scenarios can bring in additional challenges. Our scientific journey is all about understanding these nuances and using the tools at our disposal to navigate them effectively. Keep your curiosity alive as we head towards our final topic. Congratulations, students, for making it this far on our exploration of the Nernst equation. As we wrap up, let's reflect on the significance of this equation and its lasting legacy. The Nernst equation has had a profound impact on the field of electrochemistry, shaping the way we understand and manipulate electrochemical reactions. Beyond its direct applications, it has laid the foundation for more advanced concepts in the world of chemistry and physics. It's exciting to think about the endless possibilities that this equation has unlocked and the discoveries it continues to inspire. In labs and research centers around the world, scientists are building on this knowledge, delving deeper into the mysteries of chemical reactions and pushing the boundaries of what we can achieve. So, as you continue your journey in the world of science, remember that the Nernst equation is just one stepping stone in a river of knowledge. Embrace the challenges, ask questions, and keep pushing the boundaries of what you can learn and discover. Thank you for joining me on this exhilarating ride, and keep the spirit of scientific curiosity alive in your hearts. Until next time. Hello, dear students. Today, we're delving into the fascinating world of electrochemical reactions and exploring a powerful equation known as the Nernst equation. But before we get into the equation itself, let's first understand the concept of the reaction quotient, represented by Q. This quotient resembles the equilibrium expression but uses concentrations present in the reaction mixture at a specific moment. Now, here's where things get truly intriguing. By combining increment G equals NFE, as seen in equation 20.11, with equation 20.15, we arrive at NFE equals NFE degree plus RT lane Q. Don't worry if that looks a bit complex, we'll break it down step by step. This equation plays a crucial role in the Nernst equation, which you're about to meet. The Nernst equation, represented as E equals E degree RT NF lane Q, gives us insights into the potential difference, E, across an electrochemical cell. So, get ready to uncover the mysteries behind electrochemical reactions and the driving forces that make them tick. Welcome back, eager minds. Let's take a closer look at the Nernst equation's significance in the realm of electrochemical cells. This equation isn't just a mathematical formula, it's a gateway to understanding the behavior of these cells. By using the Nernst equation, we can bridge the gap between the standard electrode potential, E0, and the actual potential, E, across a cell. As concentrations change within the cell, the equation helps us predict how these changes influence the cell potential. Remember, the Nernst equation connects the dots between the concentrations of species involved in the reaction and the potential difference across the cell. This connection is vital because it allows us to explore the relationship between free energy change, delta G, and the cell potential. So, as we journey through this intricate world of electrochemistry, keep the Nernst equation in your arsenal of knowledge. Greetings, curious learners. Today, let's uncover the real-world applications of the Nernst equation that extend beyond textbooks and classrooms. This equation isn't confined to theoretical realms, it has a strong presence in various fields. Imagine being able to design electrochemical sensors that rely on the Nernst equation's principles. These sensors play crucial roles in detecting and measuring specific ions in solutions, contributing to advancements in healthcare, environmental monitoring, and more. The equation's magic also extends to potentiometric measurements, helping us determine pH levels accurately and efficiently. Beyond that, the Nernst equation provides insights into the fascinating world of biological systems, where redox reactions govern processes ranging from cellular respiration to neurotransmission. So, as you absorb the knowledge we're sharing today, remember that the Nernst equation is a tool that empowers innovation and exploration in countless ways. Hello, aspiring chemists. As we approach the end of our journey into the Nernst equation, let's ensure you're equipped with the tools to master its application. Applying this equation effectively requires a step-by-step approach. Begin by understanding the constants involved: R, the ideal gas constant; T, temperature in Kelvin; and F, Faraday's constant. These constants add layers of meaning to the equation's components. When solving problems, pay close attention to concentration changes and their impact on cell potential. Don't let the math intimidate you. Remember that each calculation reflects a real-world scenario. Whether it's determining the pH of a solution or predicting the behavior of an electrochemical sensor. So, as you continue your journey through the world of chemistry, carry the insights from the Nernst equation with you, and let it guide you toward unlocking the mysteries of electrochemical reactions. Hello, dear students. Today, we're delving into the intriguing realm of electrochemical reactions and a powerful equation that helps us understand them better. The quantity we're discussing here is called the reaction quotient, often denoted as Q. It's a lot like the equilibrium expression, but it represents the concentrations in the reaction mixture at a specific moment. Now, if we recall delta G equals -NA from equation 20.11, we can insert this into equation 20.15. Doing so yields an interesting result. -ANAF equals -ANAF degree plus R natural log Q. But what does this mean? Well, by solving this equation for AA, we arrive at a significant equation known as the Nernst equation. AA equals AA degree, R, ANAF, natural log Q. This equation is a vital tool in understanding electrochemical processes, and it reveals the relationship between electrode potentials, equilibrium constants, and reaction conditions. Imagine the applications and implications of this equation as we journey through the world of electrochemical reactions. Let's proceed to the next topic and explore further. Hello again, dear students. Today, we're delving into the realm of electrochemistry and the fascinating Nernst equation. Our journey continues with an exploration of how electron transfer affects the potential of electrochemical cells. Let's take a closer look at an example involving zinc and copper ions. In this scenario, 2 electrons are transferred from zinc to copper ions, leading to a standard electromotive force, EMF, of plus 1.10 volts. Now, at a temperature of 298 K, the Nernst equation comes into play. It allows us to calculate the cell potential based on ion concentrations. The equation is E equals E naught minus open parenthesis 0.0592 volts divided by N close parenthesis times logarithm of Q close parenthesis, where E naught represents the standard EMF, N is the number of electrons transferred, and Q is the reaction quotient. Remember, pure solids are excluded from the expression for Q. Now, according to equation 20.19, the cell potential changes with alterations in the concentrations of ions. Specifically, as the concentration of copper ions, Cu², increases and the concentration of zinc ions, Zn², decreases, the EMF of the cell increases. Let's put this into context with an example. If Cu² concentration is 5.0 m and Zn² concentration is 0.050 m, we can plug these values into the equation to find the new cell potential. By substituting the numbers, we get E equals 1.10 volts minus 0.0592 volts times 2 times logarithm of open parenthesis 0.050 divided by 5.0 close parenthesis, which ultimately equals 1.16 volts. Keep in mind, this equation and concept play a crucial role in understanding electrochemical processes. Now, let's move forward and explore even more captivating aspects of electrochemistry. Hello, dear students. Today, we're delving into the intriguing realm of concentration cells and their role in generating cell electromotive force, or EMF. In the voltaic cells we've explored earlier, you might recall that the reactive species at the anode and cathode were distinct. However, an essential concept here is that the cell's EMF is influenced by concentration. Surprisingly, we can create a voltaic cell using the same species in both half cells, as long as their concentrations differ. When these concentrations vary, a cell can still generate an electromotive force, and we refer to this type of cell as a concentration cell. Let's journey further and uncover the details of how concentration differences play a pivotal role in creating this EMF. Hello, students. Today, we're delving into the intriguing world of electrochemical reactions and focusing on a fascinating example of a concentration cell. Let's start by understanding the components involved in this setup. In Figure 20.14, you can see the diagram of the concentration cell we'll be discussing. This cell comprises 2 half cells, each containing a strip of nickel metal. The key difference between the 2 half cells lies in the concentration of the Ni2+ solution they're immersed in. One half cell contains a nickel metal strip submerged in a 1.00 × 10⁻³ m solution of Ni2+ ions, while the other half cell's nickel strip is placed in a more concentrated 1.00 m solution of Ni2+ ions. Both half cells are connected through a salt bridge and an external wire connected to a voltmeter. Now, let's explore the intriguing reactions occurring in this concentration cell. Alright, dear students, let's delve into the heart of this concentration cell, by examining the anode and cathode reactions taking place within the 2 half cells. At the anode, which is the half cell with the less concentrated Ni2+ solution, we have the reaction Ni's undergoing oxidation, releasing 2 electrons and forming Ni2+, Aq. On the other hand, at the cathode, which is the half cell with the more concentrated Ni2+ solution, we see the reduction of Ni2+, Aq, ions. In this process, Ni2+, Aq, gains 2 electrons and gets reduced back to solid Ni metal. Interestingly, the reactions in the two half cells are essentially the reverse of each other, maintaining the overall electrical neutrality of the system. Both of these reactions have a standard reduction potential, E degree red, of -0.28 volts, giving us a valuable insight into the behavior of this concentration cell. Let's take a moment to uncover a crucial aspect of this concentration cell's behavior: calculating the cell potential. Interestingly, even though the standard EMF of this concentration cell is 0, E degree cell equals 0 volts, there's more to explore. The relationship between the standard cell potential, E degree cell, and the standard reduction potentials, E degree red, of the cathode and anode reactions holds a key to understanding this. The equation E degree cell equals E degree red, cathode, E degree red, anode, allows us to determine the cell potential. For our concentration cell, plugging in the values of E degree red, -0.28 volts, for both the cathode and the anode reactions gives us an intriguing insight into the equilibrium and balance between these reactions. Keep in mind that while the standard cell potential is 0, the underlying electrochemical processes are far from mundane. As we wrap up our exploration of concentration cells, it's time to reflect on the valuable insights they offer. These cells provide us with a unique perspective on equilibrium and electrode potential. The variations in concentration gradients within the half cells play a significant role in driving these electrochemical reactions. This concept of concentration gradients is not only central to our understanding of concentration cells but also holds relevance in various real-world scenarios. Concentration cells play a crucial role in corrosion studies, allowing us to comprehend the factors contributing to the deterioration of materials. This underscores the practical applications of electrochemistry in our everyday lives. So, students, as we conclude our discussion on concentration cells, remember that even seemingly simple systems can reveal intricate and insightful aspects of chemistry. Welcome, dear students. Today, we delve into the intriguing realm of electrochemical cells, specifically focusing on how they function under non-standard conditions. We're about to uncover the fascinating world of ion concentrations and their impact on cell operations. Imagine a scenario where the concentration of Ni2+ ions isn't a standard 1 m in both half cells. This variation in concentrations leads to remarkable changes in how the cell operates. Let's explore the details step by step. As we dive deeper into the mechanics, we discover a crucial connection between Ni2+ ion concentrations and how the cell operates. In this specific case, the equilibrium point is reached when the amount of Ni2+ ions at the anode, the half cell with the more dilute solution, matches the number of Ni2+ ions at the cathode, the half cell with the more concentrated solution. To achieve this equilibrium, fascinating reactions take place, which determine the functioning of the cell. Let's understand the intricacies step by step. Alright, my curious learners, let's explore the reactions occurring at the anode and cathode. In the half cell with the more dilute solution, the anode, the fascinating process of oxidation occurs. Here, solid Nis undergoes oxidation, leading to the release of electrons. Meanwhile, at the cathode, which contains the more concentrated solution, reduction takes place. Ni2+ ions from the solution are reduced, gaining electrons to form solid Nis. As these reactions unfold, electrons flow, creating a circuit and enabling the cell to function. And what's the big picture? The overall reaction results in a balance between Ni2+ concentrations in the two half cells. Now, my inquisitive students, let's delve into the significance of achieving equilibrium in this electrochemical setup. Equilibrium is reached when the Ni2+ concentrations in the anode and cathode match, indicating a delicate balance between oxidation and reduction reactions. This balance is essential for maintaining the flow of electrons and the overall functioning of the cell. Remember, it's the movement of ions between the half cells that creates the electrical potential necessary for the cell's operation. With this equilibrium in place, we witness the mesmerizing interplay of chemical reactions and energy conversion. As we conclude our exploration, students, we have uncovered the intricate workings of an electrochemical cell operating under non-standard conditions. The equilibrium point, where Ni2+ concentrations in the two half cells match, plays a pivotal role in determining how the cell functions. This example highlights the significance of understanding ion concentrations and their effects on electrochemistry. Remember, this knowledge opens the door to comprehending a wide range of electrochemical processes that shape our world. Keep your curiosity alive, and let's continue our journey of discovery in the realm of science. Welcome back, dear students. Today, we're delving into a fascinating concept known as the concentration cell. Brace yourselves for an electrifying journey. In a concentration cell, something truly remarkable happens. Despite the standard potential, E degree, being 0, an electromotive force, EMF, of around 0.09 volts is generated. How is this possible, you ask? Well, it's all due to the power of concentration differences. Imagine two half cells, each with a different concentration of species. This concentration gradient acts as the driving force, leading to the creation of EMF. As the concentrations in both half cells eventually equalize, our trusty friend Q becomes 1, resulting in an EMF of 0. But don't let that fool you. The journey through concentration cells is nothing short of electrifying. Greetings, eager minds. Let's take a closer look at the mesmerizing process that unfolds within a concentration cell. Picture this. Two half cells, each housing a unique concentration of substances. In the realm of redox reactions, magic is in the air. Electrons embark on a journey, flowing from the region of higher concentration to the one with lower concentration. This electron dance drives the creation of our coveted EMF. As the concentration disparity diminishes over time, equilibrium beckons. Equilibrium is reached when the concentrations level out in both half cells, leading to a peaceful EMF of 0. The sheer elegance of this process reminds us that even the subtlest of gradients can orchestrate captivating performances of energy exchange. Hello again, my curious learners. It's time to unlock the secrets of the Nernst equation and its enchanting connection to concentration cells. This equation is a gem that reveals the delicate dance between EMF and the ratio of concentrations. As the concentrations shift, so does the EMF, creating a symphony of energetic exchange. But that's not all. Temperature and gas constants play a role in shaping this equation too, allowing us to explore the impact of temperature on our concentration cells. Oh, and let's not forget our steadfast companion, the Faraday constant, which brings charge transfer into the mix. Through the Nernst equation, we gain a deeper understanding of the dynamic interplay between concentration, EMF, and temperature in the captivating realm of concentration cells. Greetings, knowledge seekers. Let's uncover the practical side of concentration cells with a peek into their versatile applications. The world of science and engineering benefits greatly from the insights concentration cells provide. Imagine using these cells to combat the ravages of corrosion. By strategically setting up concentration gradients, we can safeguard metals from deteriorating forces. And what about batteries? Yes, concentration cells contribute here too, playing a pivotal role in energy storage systems that power our devices and light up our lives. But wait, there's more. Concentration cells lend their talents to sensors and pH measurement devices, enhancing our ability to explore and understand the world around us. So, remember, the power of concentration cells goes beyond theory. It's a force driving innovations that shape our modern world. Welcome back, students. Today, we're delving into the fascinating world of potential difference and its implications in various biological and chemical contexts. Our journey begins with the concept of generating potential by leveraging concentration differences. This phenomenon forms the foundation for the operation of pH meters, which play a crucial role in measuring the acidity or alkalinity of solutions. These meters work by capitalizing on the potential difference created due to varying ion concentrations. Moving on, Let's explore a captivating example in the realm of biology. Nerve cells in the brain exhibit an astonishing ability to generate a potential across their membranes. This is achieved through the manipulation of ion concentrations on either side of the cell membrane. The result? A potential difference that's fundamental to nerve cell function. And speaking of unique adaptations, let's talk about electric eels. These remarkable creatures employ specialized cells known as electrocytes to generate brief yet intense pulses of electricity. Just like our pH meter and nerve cell examples, electric eels leverage potential difference based on concentration gradients. This electric shock serves to immobilize prey and deter potential threats. But the intrigue doesn't stop there. Our exploration extends to the intricacies of electrochemistry and regulating mammalian heartbeats, a topic we'll dive into next. Hello, students. Today, we're delving into the intriguing world of voltaic cells and ion movement. Picture this. The interior of a cell and the extracellular fluid, ECF, together create what's known as a voltaic cell. A negative potential here tells us that it requires energy to transport potassium ions, K+, into the intracellular fluid, ICF. The interplay of ion concentrations between the ECF and ICF doesn't just stop there. It's the driving force behind changes in the electromotive force, EMF, of the voltaic cell. This EMF change is like a rhythmic dance, and we'll uncover its cyclic nature in just a moment. But first, let's move on to an exciting aspect of cell functionality. Null. Hello again, students. Let's zoom in on the mesmerizing EMF cycles and dive into the details of Figure 20.16. As we've been exploring, the EMF, the electromotive force, experiences a rhythmic cycle. This cycle holds the key to understanding the changes in energy within the cell and ECF. Figure 20.16, which you'll find in your textbooks, beautifully captures this cyclic dance of EMF. The shifts in ion concentrations we've been discussing bring about these EMF changes. These variations are like the heartbeat of the cell, pulsating in harmony with the intricate processes happening within. Keep your focus, as we're about to unlock the final layer of this captivating journey. Greetings, curious minds. We've traversed through the captivating world of EMF cycles, ion movement, and cell dynamics. So, what's the big picture here? These EMF cycles aren't just random fluctuations. They're the very heartbeats of cellular processes. The intricate dance between energy and ion movement is the foundation of numerous cell functions. As we peer deeper into this realm, who knows what other secrets of cell dynamics we might uncover? The potential for future discoveries is both exciting and humbling. With that, we wrap up our journey today, but remember, our exploration of the incredible world of science and nature never truly ends. Until next time, keep your curiosity alive. Welcome back, students. Today, we're going to delve into a crucial aspect of our bodies, the heart's rhythm and its connection to pacemakers. Our heart's rhythmic contractions are controlled by specialized cells known as pacemaker cells. These cells play a vital role in maintaining a steady heartbeat. Unfortunately, sometimes pacemaker cells can malfunction due to diseases or injuries. But fear not, medical science has come to the rescue. We have a remarkable solution: the surgical implantation of an artificial pacemaker. This artificial device contains a small battery that generates precise electrical pulses. These pulses act as the heart's natural pacemaker, triggering the contractions that keep blood flowing throughout our bodies. The synergy of biology and technology is truly awe-inspiring. Now, let's journey further into the world of scientific marvels. Greetings, curious minds. Today, we're going to unveil the intricate process of implanting an artificial pacemaker. Picture this. A skilled surgical team places the pacemaker beneath the skin, typically in the chest region. The placement is strategic, ensuring optimal connection to the heart's electrical pathways. Once situated, the pacemaker works tirelessly to generate electrical pulses. These pulses mimic the natural heartbeat, causing the heart muscles to contract rhythmically. Medical professionals closely monitor and adjust the pacemaker's settings to ensure proper pacing and rhythm. It's truly remarkable how technology collaborates with our bodies to maintain vitality. Now, let's explore more fascinating horizons. Hello again, eager learners. Today, we're shedding light on the energy source that powers our artificial pacemakers. Within this incredible device resides a small yet potent battery. This battery serves as the heartbeat's driving force, generating the essential electrical pulses. It's the pacemaker's lifeline, ensuring consistent and reliable function. Just as we recharge our devices, monitoring the battery's levels is crucial to maintain the pacemaker's operation. This fusion of biology and engineering showcases how scientific advancements enhance the quality of human life. Now, let's continue our journey into the realm of scientific wonders. Greetings, inquisitive minds. Our exploration today has unveiled the astounding impact of technology on healthcare. Artificial pacemakers stand as true pioneers in medical innovation, transforming lives and restoring the rhythm of the heart. With the ability to simulate normal heart function, these devices gift patients with an improved quality of life. From maintaining active lifestyles to pursuing daily routines, pacemakers empower individuals to thrive. And remember, the story of progress doesn't end here. Ongoing advancements in medical technology promise even more remarkable achievements on the horizon. As we conclude today's journey, let's celebrate the wonders that emerge when science and compassion unite. Hello, dear students. Today, we're going to explore a remarkable aspect of medical science: electrocardiography, or ECG for short. Back in the late 1800s, scientists made a groundbreaking discovery. The electrical impulses responsible for the contraction of the heart muscle are strong enough to be detected on the surface of the body. This discovery laid the foundation for a revolutionary technique in medical monitoring. What is this technique, you ask? Well, it's electrocardiography, a non-invasive method of keeping an eye on our heart's activity. How does it work, you wonder? By placing a complex array of electrodes on the skin, we can measure the voltage changes that occur during each heartbeat. Let's move on to the next topic to delve deeper into this captivating topic. Welcome back, students. Now that we have a general idea of how electrocardiography works, let's take a closer look at what an actual electrocardiogram, or ECG, looks like. Imagine a graph that shows the voltage changes during the different phases of the cardiac cycle. That's what an ECG is all about. You'll notice peaks and valleys on the graph that represent various electrical events occurring in the heart. These events include the P wave, QRS complex, and T wave. Each of these components tells us something important about the heart's activity. So, the next time you see an ECG, remember that it's like a visual snapshot of your heart's electrical dance. Null.